Avui comptem amb el genial Chris Brownell, que ens parlarà del joc Una zona creativa pels matemàtics. Vull per sobretot agrair la participació desinteressada del Chris per fer aquesta xerrada. El Chris és professor associat de la Universitat de Fresno Pacific, en Califòrnia. És consultor, director d'un programa educatiu sobre matemàtiques i STEAM i es defineix com a fan de les matemàtiques recreatives, del joc, de l'art i de les matemàtiques. També és autor del magnífic llibre Math Recess. Recordeu de mantenir els micros tancats i qualsevol pregunta o comentari podeu fer servir el xat. També us recordo que la sessió serà gravada. Sense més, us deixo amb el Chris. Gracias y que gaudiu. Hola de nuevo a todos. Hoy tenemos la tercera sesión del ciclo de conferencias internacionales del MMACA. Hoy contamos con el genial Chris Brownell, que nos hablará del juego Una zona recreativa para los matemáticos. Por encima de todo, quiero agradecer la participación desinteresada de Chris para hacer esta charla. Chris es profesor asociado de la Universidad de Fresno Pacific, en California, consultor, director de un programa educativo sobre mates y STEM y se define como fan de las matemáticas recreativas, del juego, del arte y de las matemáticas. Es autor del magnífico libro Math Recess. Recordad dejar los micros cerrados y cualquier pregunta o comentario podéis utilizar el chat. También os recuerdo que la sesión se grabará. Sin más, os dejo con Chris Brownell. Gracias y que disfrutéis. Hello again, everybody. Today we're having the third of the MMACA's international sessions. Today we have the great Chris Brownell, who will talk about playfulness, a mathematician's creative zone. Overall, I want to thank Chris for his participation in this talk. Chris is an associate professor at the University of Fresno Pacific in California, consultant, director of Math and STEM Education Program, and as himself says, a huge fan of joyful mathematics, play, art, and math. He is also one of the authors of the wonderful book, Math Recess. Remember, please, to keep your microphones muted, and you can use the chat for any questions or comments. I remind you that this session will be recorded. Without any further, I leave you with Chris Brownell. Thank you, Chris, and enjoy.
Thank you, Sergio. I appreciate the kind words, the very generous words of yours. Buenas tardes a todos y buena tarde. I would like to talk about this evening, or this, for me, it's very early. Well, it's not very early, but it's about 10 o'clock in the morning, 10 a.m. And I would like to talk about playfulness as sort of an approach to thinking about mathematics. And in so doing, I'd like to encourage everybody to embrace playfulness for its value in the doing of and understanding of and the evangelizing for a mathematical approach to life. So I have a quick presentation I put together on PowerPoint, and if I can, I'm going to try and make this work. Please bear with me, as I don't always get these things right. So seems, yes, so far so good.
Yes, perfect.
And now if I switch, so now perfect. All you see is bubbles and playfulness.
Yes.
Okay, so again, I'd like to I really hope this is a very short talk, and we can go and all have more fun and play with some ideas that I might present. First off, just to round out a little bit of who I am, I co-authored a book called Math Recess: Playful Learning in an Age of Disruption with Sunil Singh, who also has written a book called Pie of Life. We wrote the book with the goal of helping to rehabilitate the view most people have of the subject we love, which is mathematics. And we also did it. We wrote the book as well because it was an endeavor. It was a joyful endeavor on our part. It was not just work. We wanted to do so. We had a grand time talking about the ideas. The original title for the book really was Mathematics for the Beach, the Bar, and the Barbecue. Barbecue being something Californians and Canadians share. I hope that's true of Catalan as well. We chose the recess metaphor for a reason, though. And that was because here in the United States and in North America, as a child, growing up when you're in school, most children find recess time at school to be the more enjoyable piece of schooling. At least it was for the two of us. And so we were locked in our own heads in many ways. We loved the time out at recess. And one of the things we both agreed about recess was part of the joy was being able to play freely, run about, and change the rules of your game as you were playing. And that and those rule changes were always sort of predicated on making the game we were playing better. And we found that we think of that, and I truly believe that is at its heart what disruption is about. It's about moving things along. I'd also like to couch or surround this talk today with some ideas from one of my other favorite books, which is How Mathematicians Think, Using Ambiguity, Contradictions, and Paradox to Create Mathematics by William Byers. Strongly, highly recommend this book. Pardon me. In his book, the last chapter, in fact, asks the question, is math algorithmic or creative? And he places in there, sandwiches that question afterwards, the bottom half of the sandwich, with the statement, I've been describing mathematics as an activity that is dynamic and creative, pulsating with life of the mind. And the top half of the sandwich with a longer statement that says mathematics is the model for how the natural world works. It is the model for how human beings work, for how we think, for our notion of truth. Our view of mathematics has a profound effect on our view of ourselves and therefore on the kind of people we shall be in the future. Now, I say that in this context because while that doesn't sound playful, it certainly gets at the heart of the creative space that mathematicians live in. Mathematics is, in Byers' opinion, a creative act. It is a place. It's a thing that we do as humans. It's not just something we discover as though all these ideas exist a priori, but instead we also create, we co-create these ideas. I don't really want to get into that long argument about should it be, is mathematics totally created or is it discovery? There are lots of people willing to have that. I'm not going to go there, but I want to think about how mathematicians use their playfulness to create. And in so doing, I'd like to put that in the context of two very active mathematical minds. The first, I'd like to look at is Charles Lutwidge Dodgson, who lived from 1832 to 1898. He was a very playful man, a mathematician in his own right, in his own time, not necessarily known by everyone today by this name, and I'll leave his other names out for a moment because I want to think about the mathematics and how the mathematics this man created. Interestingly enough, the drawing that you see in this slide is a self-portrait that he made. He captioned it, "What I look like when I lecture." What he's like, you can tell he's a man who takes himself only marginally seriously, and believes that he ought to maybe sometimes just put a hand over his mouth. And the second person I'd like to think about in our time together is John Horton Conway, who lived from 1937 until just this year. So Dodgson and Conway will be sort of the two figures that I'd like to create our time or talk through our time together with. They are separated by decades, but they are connected in their playful attitudes towards mathematics. They both were known to be quite playful and even silly at times, if that word translates well. Sergio, this is where I need your help.
Me? You can ask to everyone. Don't worry.
Okay, we'll ask everyone. I'm going to adapt a problem from a collection of problems known as pillow problems for dealing with when you are trying to hone in or hem in your thoughts while you lay in bed, by Charles Dodgson. So this problem is not stated in the way that I will, but I'd like to state it in a slightly different way. I'd like you to choose 3 positive integers. Just
okay. Should I tell you or not?
You know what? Let me work through this. Let me give you a description, and maybe everybody will do that. Choose your 3 integers.
Okay.
And would you write them down for me, Sergio?
Okay.
17.
Okay. And then if you have a calculator handy, if you haven't chosen particularly large integers, I'd like you to square each of those 3.
Okay. Let's do it all together, right?
Yeah.
Milo, can you translate it in the chat, please?
I wonder. I'm going to try and do something else along the way. I think I can.
We lost your presentation, Chris.
That's good. You were supposed to.
Okay. But we cannot see the instructions.
Okay, well, right now just choose 3 integers and square them.
Okay.
And then add those 3 together. Can you give me the 3 you chose, Sergio?
Yes, I chose 2, 5, and 6.
2, 5, and 6. Can you see my screen now?
Yes, the Excel file, yes.
In Excel, it's a Google Sheet. This Google Sheet is available to everyone. I
Yes.
earlier chose 5, 10, and 8.
Mhm.
So you've chosen 3 integers. I've chosen 3 integers, right? We
Yes.
both squared them.
Yes.
Squared each one. Your 2 became 4. My 5 became 25. My 10 became 100. Your 5 became 25, etc. Right?
Yes.
And I added them together. Your 3 squares add up to 65.
Yes.
My 3 squares add up to 189.
Mhm.
Now, I say I can always find 4 numbers, 4 other integers whose squares sum to something having a very interesting relationship with that other sum of squares.
I cannot see the relation.
You cannot see this relation? That's good. You're not supposed to yet. I'm talking about this value and this value.
Yes. Okay. Someone says is 3 times.
Wow. Is that true of your collection and my collection? Have I lost you? Are we still together?
I lost connection for a moment, so I didn't hear anything from the last 30 seconds.
Okay,
Sorry.
I did. That's all right. This is the way these things go, right? We always have these interesting little things. So somebody in the chat, did somebody say times 3? I see that. I don't see what those other words, what all of those other words are. So is it true that this result is always true? And if so, can you prove it? Can you state that as a conjecture? So is it always possible to find 4 other positive integers whose sum of squares have that relationship, which we now have identified as being 3 times the original sum? If you have shared out the PowerPoint, down at the bottom is a link to this spreadsheet. I have created this spreadsheet in a particularly mysterious way. And you're welcome to add numbers in at the beginning. And then you are, so anybody can go into this spreadsheet, I believe, and add their values. Or you might be able to look at these and see if you can figure out how what those four integers are.
Chris, can you add some other numbers in the sheet? Okay, thank you.
Yeah.
Okay.
I suppose we could always.
Can you add 1, -1, and 0?
1, -1?
Yes.
-1?
And 0?
Does anyone, I don't know, I cannot see the chat, so I don't know if anyone has postulated or predicted what might these, I've labeled them as M1, M2, M3, and M4 mystery numbers are. How do you find these mystery numbers?
Should I read what the chat is saying, Chris?
Sure.
So Nestor is saying 3 open brackets 8 squared plus b squared plus c squared. Well, can you not read the chat? Can you
I can now. I've.
Oh, you are. Okay, lovely.
Excellent.
Oh.
Nice. Tiffany asks, I thought they had to be positive. Why don't they have to be positive suddenly? Will they work if they're all negative? They seem to. Oh, that's right. We are squaring. We don't have to worry about it. Now I'm finally figuring out how I can both present the spreadsheet and read the chat. Nestor. Nestor has hit upon it. It's a simple identity. So I'd like to stop presenting that and look at you if I could. I have been wanting, so if this is interesting to you, it was interesting to Charles Dodgson enough that he wrote it into a book of 72 other problems that he used to clear his mind as he was trying to sleep on some evenings. My question is, can we build, and I don't have an answer for this, but I keep playing with it. I want to build an actual puzzle of pieces that can be dissected and laid on top of each other. So one set of 9 squares that can be dissected, and one set of 4 squares that can be dissected in some way that they can then be repositioned so that they coincide on top of each other. Hey, Mark, I didn't know you were coming. Nestor, you just happened upon it by chance? That's awesome. Okay, I think it's time to move on. I will leave you with a few plaguing questions, I hope, and just enough to. Is it pure algebra? Okay. Now, let me switch back and continue with my little presentation, hoping not to take too long on any one little plaguing thought. So next, another problem from the same collection Dodgson put together. A bag contains a counter which is known to be either black or white. Then we place a white counter into that bag. So now there are two counters in it. We shake the bag up. You reach in and grab a counter and reveal that it is white. What are the chances that the next time I reach into the bag, I also draw out a white? It's the same as it was in the beginning. So,
okay. Milo is translating the problem to everyone. Okay.
Okay.
And some time to think.
I will not push on. I haven't said a thing. How can I be right? I just asked a question. Oh, Alex, I see. Mark says Alexandra may be right. Oh, we have a disagreement. 1/2 between Sergio and Alexandra, they seem to think 1/2, but now, forgive me if I mispronounce, Oriol says 2/3 with a no. The problem of the 3 doors. Very, very nice. Hey, Dave Martin. Good to see you. Monty Hall. See, that was my thought as well. When I saw this problem, is like, this is the Monty Hall problem in disguise, isn't it? It is not provoked. Randomness rules. And the assumption is as well that black or white for the first unknown counter is also randomly decided. I just think this problem is too fun. Yes, Mark. I'm going to not answer any more questions about it because that's the mean sort of person I am. And I'm going to move on. I've been hiding from you tidbit of information. Some of you saw it early in or knew this already, but Charles Lutwidge Dodgson is the given name to the author of the Alice in Wonderland books, Lewis Carroll. Dodgson actually created the nom de plume of Lewis Carroll by looking at his first name and his middle name and translated them into Latin and reorganized them, or translated them into, I think Latin, then retranslated them back into English and reordered them and hence he became Lewis Carroll. It's not always talked about. I mean, maybe in our circles, in the circles of the Math Museum of Catalan, that Dodgson wrote quite a large number of mathematical books. Most of them had to do with Euclidean geometry, but also he had a theory of determinants and wrote on logic and probability. He was among the first to use the idea of a truth table in examining logical statements in writing, and he also applied a theory of tree diagrams to logic problems. And if you read Alice in Wonderland, not just for enjoyment, which is hard to do, but when you do read it, the reason it is so enjoyable is because he plays with the logic that is inherent in our language, in the language that he chose. And he massages that language and he massages meaning in fun and interesting ways. And it's because of his mathematical creativity that he's capable of pulling that off in stories. It's not just that he was a super creative mind, but he was also he ran with logical connections and twisted them just a little bit at the end. And that's what makes it such an enjoyable series. After So Dodgson lived until about the turn of the last century, 1898. He unfortunately died from complications due to a respiratory disease. He caught a cold. His doctor sent him home to bed, and 2 days later he succumbed to the cold just suddenly at age 68 or 66. And it was sudden and tragic to see his loss. Now I'd like to move to another famous creative mathematician, John Horton Conway, also from England, though he's from Liverpool. He was educated at King's College in Cambridge. He would have described his early career as a mathematician as being frustrating to him. He earned his doctorate early. Well, not early. He earned his doctorate in the late 50s, 1958 or 59, and struggled for a long time, or for a while anyway, to get his feet on the ground in the mathematical research world. And until 1965 or so, he was introduced to this problem known as sphere packing in 24-dimensional space. The picture in this slide is actually a 2-dimensional representation of a 3-dimensional net of a 4-dimensional sphere packing problem. If you can imagine how complicated that, or complex, not really complicated, but complex that picture is, and then raise that to the 6th power, and you're in the 24th dimension. The nature of those realities, those truths, become quite complex and difficult to visualize, I would believe. I can't picture them. I haven't given myself to do so. But that colorful image is what's known as a Leech lattice in 4-dimensional space. And he solved the problem of the Leech lattice in 24-dimensional space. What he loved about having done that, from what I've read and heard from listening to several of his talks, was that he, having solved that problem, he was set free of the burden of ever having to do anybody else's mathematics. And he was released because of this, to let his mind wander and create in areas that interested him. And he was a great fan of games. He invented several both mathematical and physical board games. He created, there's one game that he's probably most famous for, and that's the game of life. The game of life is what's known as a cellular automaton, and what you're looking at is an example of the game of life. In the game of life, you turn on pixels in a square lattice. You picture a square lattice where some of the squares are colored black or turned on like pixels, and others are left off. The ones that are on are considered alive, and the ones that are off are not alive. And then through some very simple rules for how life occurs in this system, the cells at any one stage get colored or recolored or uncolored based on those rules. Interestingly enough, this image that you're seeing, where these things seem to be walking across the stage, is an occurrence from this random sort of behavior. It's deterministic, but it is quite random. Cellular automata was a brand new field of mathematics, though. It didn't exist before Conway decided to play games with it and generate rules for it. And other people came along and changed those rules and altered those rules and have discovered new things. Notably among them is Stephen Wolfram of the Wolfram Research Institute, MMACA language. He created a book, a whole massive book. Many of you may have read it, The New Kind of Science, based entirely on cellular automatons and automata. And he is very much, which is very much indebted to the work of John Conway. I'd like to show one more. I'd like to give everybody the opportunity, though, to sort of play another game of Conway's, and that's the game of Sprouts. Sprouts, we talk about in Math Recess. It's a simple two-player game, and in this two-player game, the object is, as always, to win. It's played very simply. A few simple rules. You start with some dots on a sheet of paper. Both players have a pencil. You take turns connecting dots by lines. Lines can be curves. They don't need to be straight. So lines are defined by their endpoints, not by their shape. And the lines have to meet a few simple criteria. One, no line may cross another line. Two, no line may represent the fourth connection to any dot. That's the most troubling one, I think. You have to think your way through that. You can have 3 connections, but not 4. One, you can have 0 connections to a dot, 1 connection, 2, 3, but not 4 or more. A line may connect a dot to itself. So you can draw a loop. After drawing each line, that same player has to place a new dot somewhere on that line. They get to choose, but it goes somewhere on that line. And the game ends when there are no more lines that can be drawn. The winner is the player who drew the last line and dot. Let me show you a very short game that was played. You have 2 dots. Player 1 connects those 2 dots and puts a third dot on that line that he drew or she drew to connect them. Now it's player 2's turn. Player 2 connects this dot all the way around to itself. Right? And then then places a dot on that line. That's a perfectly legal move. You've got a dot connected to itself. But notice that dot at the bottom now has 3 connections to it. That dot can no longer be played on. Then in the third iteration, player 1's turn, and he or she comes along and places this loop that kind of goes off in the inside, has the red dot placed on it. That connects the first new dot to one of the original dots, and then places yet another dot on that line. Then the fourth move is legal. And at this point, this game is over. The person who played this line and that dot have won, and that is the end of the game. I'm going to stop displaying that, and I'm going to ask, is that misunderstood, or is it well understood? How can I clarify that game? Oh, I think the rules might have to change a little bit to make it an ending game in 3 dimensions. That's an interesting question, Nestor. Is it optimal to be the first player or the second player? So,
Chris, you have some questions in the chat and some interesting things.
okay. I'd love to hear them. Let me.
Yes.
I saw Nestor's.
I don't know if you can read the chat, but
I should.
Guido asks, why don't you make a circle connection of the last green point?
Really good question. The last green point, meaning the one in the very center. That's because if you make a circle connection to that green point will have 4 connections made to it. There will be 4 places of eminence. Even though it's one line, there will be 4 connections that connect to that point. Does that make sense, Guido?
Yes. Another question from Nestor is, I'm wondering if this game is a never-ending one in 3 dimensions.
I wonder that too.
Okay.
I think in 2 dimensions, it has been shown that the game will end. That there's no way to turn it into an infinite game in 2 dimensions.
And is there always an ending?
In 2 dimensions.
In 2 dimensions.
Yes.
Okay. So that means that there is a winning strategy.
Yes. The question is, can you find it? Also, is there another question that I find fascinating is, do all games of the same number of original points have the same number of turns played. Wow, Mark and Nestor are having a grand conversation. It's great. Okay, I am conscious of the time. I don't want to play too much. I want to leave you with as many plaguing thoughts as I possibly can, because that's my nature. I'm better at asking questions than answering them all the time. So if I could, I'd like to conclude with a couple of thoughts. Mathematics is a playground in the mind, right? Playgrounds are often characterized by those games whose rules are made up by the players. I love Calvin and Hobbes, the cartoon, the comic strip. I don't know if Calvin and Hobbes makes, if it translates nicely into other languages besides English, but Calvin's the boy and Hobbes is the tiger. And they are constantly playing a game of Calvin ball in which the rules change at will. You can see them there. They've got croquet wickets, badminton rackets, croquet mallets, hobby horse, volleyball. Everything's available to them. The tree might even be part of the game. Children, I played games almost this haphazard as a child, and that's part of the world that we, Sunil and I, tried to put everything together for Math Recess, but also that's the vision that we have, that I have for mathematics teaching in the future, that children should view mathematics with as much abandon as Calvin and Hobbes are at playing their game. This is inherently disruptive. And it's, pardon me, but it's a hell of a lot more fun. And it's really much closer to how mathematics is accomplished. People play games. James Tanton is here in this meeting, and I recorded a podcast with James years ago in which he tells the story of how he became a mathematician and how he knew he wanted to study mathematics. And it was through playing games with the tiles on the ceiling of his bedroom at home when he was a child. He envisioned games and he made things up. And it was because of that he decided to be a mathematician. I think that's just wonderful. And finally, a couple of things I want to put out there, sobering in some ways. Both Conway and Dodgson were taken from this planet due to sudden, painful respiratory diseases. I mentioned earlier how Charles Dodgson and Lewis Carroll died of the cold. Conway succumbed to the COVID virus on April 11th this year. He'd felt ill, checked in with his doctor, who checked him into the hospital on the 8th of April, and he died and was taken from us 3 days later. So please, as you go forward into your lives and into the days of the future, the coming days, be safe and be wise about your interactions and how you are playing the game of life and playing mathematics. Don't let our inability to be in one room together physically limit your play, but instead be smart and be wise about how you interact and with whom and where. And then I'd like to just say thank you. And if you want to get a hold of me, you can find me on Twitter, cbrownlmath, or you can send me emails at mathedresearcher@gmail.com. Sergio, I sent you this PowerPoint, and you're welcome to share it with anybody who would like it. And
Okay.
that will be the end of my little talk, if that's all right.
Okay, Chris. So, if someone has any question for Chris, si algú té alguna pregunta pel Chris, la podeu fer al chat i us la traduïm fins i tot, cap problema.
Oh my gosh. See, I'm sorry. While people are coming up with their questions, I'm just now getting back through scrolling the chat. People are talking about what happens if you place sprouts on a torus? What happens if it's on a sphere?
Okay, so
you are breaking the rules in just the best way.
Okay, thank you very much, Chris. So if there's no questions, we can finish here, and hope you can join next week. It's going to be Adrian Paenza session. Okay, it's going to be in Spanish, but anyway, you can join if you want, okay? So, ho deixem aquí. Moltes gràcies al Chris. La setmana que ve tindrem a l'Adrián Paenza amb nosaltres a la mateixa hora, al mateix lloc, okay? Same place, same time, here next week. Thank you very much, and be safe, of course.
Thank you.
Thank you all. Thank you very much. Sergio, this was so fun.
You're welcome. Thank you for the session. That's been really interesting.
Hey, Kieran. Oh, wow. All kinds of people around. Thanks, James.
No worries. You can unmute your microphone and speak.
Yeah. Anybody left who wants to hurl blasphemies at me? Accusations of blasphemy. I'm open.